Section: Introduction. In this section, we discuss the impressive text generation abilities of large language models, LLMs, and their growing popularity. However, we face a major challenge with the speed of text generation. The common method, known as autoregressive models, generates text one token at a time. While this method produces high-quality results, its sequential nature limits how quickly we can generate text, especially as models become larger. Recent trends in scaling and reasoning suggest that generation speed will be a key issue for enhancing LLM capabilities. This has led us to explore alternatives to the traditional autoregressive approach. One promising alternative is diffusion large language models, DLLMs, which can potentially generate multiple tokens at once, inspired by successful image generation techniques. In our work, we question the assumption that DLLMs, like the open-source models Dream and Llama, can effectively generate tokens in parallel without modifications. We discover that the best quality is achieved by generating tokens one at a time, and attempts to leverage parallel generation result in lower quality. Therefore, the current DLLMs, Dream and Llama, do not yet match the speed and quality of autoregressive models. We illustrate the difference between autoregressive decoding and our method, adaptive parallel decoding, APD, showing that APD can generate text much faster than the slow sequential autoregressive method. This gap between what is theoretically possible and what is practically achieved opens up opportunities for new decoding methods that can utilize the parallel capabilities of DLLMs while still producing high-quality text. The main challenge we face is that when generating multiple tokens at once, we only have access to the individual probabilities of each token, which does not account for the relationships between them. Our decoding algorithm, APD, aims to increase parallelism while maintaining quality by considering the combined probabilities that reflect these relationships. In APD, we first set the generation order of the DLLM to be left to right, making it behave auto-regressively. We show that this approach can maintain or even improve quality. By using a smaller autoregressive model to evaluate which tokens generated in parallel capture the necessary dependencies, we create a new problem framework. Our contributions go beyond just the APD concept. We enhance the decoding process with practical improvements, such as key-value caching, which is typically used in autoregressive models, and we increase speed by limiting the size of the input to the model. These adjustments significantly boost the efficiency of DLLM inference. We introduce 3 adjustable parameters that allow users to balance between generation speed and output quality, catering to various application needs. Our paper demonstrates that adaptive parallel decoding significantly accelerates DLLM inference while maintaining quality across various tasks. In the following sections, we will detail the technical aspects of APD, present experiments that validate our findings, and discuss the broader implications for efficient LLM generation. In the next sections, we will define the notation we will use throughout the paper. We consider a data point as a sequence of tokens, and we will describe how a masked language model computes the probabilities of certain tokens based on others. In our work, we treat diffusion language models as masked language models, using these terms interchangeably. Section Summary. In this section, we discuss the limitations of autoregressive models in large language models, LLMs, due to their sequential text generation, which hinders speed and real-time applications. We introduce adaptive parallel decoding, APD, as a novel approach that allows for faster inference by dynamically modulating the number of tokens generated in parallel while maintaining quality, ultimately demonstrating significant improvements in throughput with minimal quality degradation. Section: Discrete diffusion language models. In this section, we explore discrete diffusion language models, DLLMs, which have recently emerged as a strong alternative to traditional autoregressive methods for generating language. These models offer advantages like the ability to generate text without relying on previous tokens and the capacity for iterative refinement. DLLMs function as masked language models that learn to reverse a process that adds noise to a clean sequence of tokens over time. They are trained to maximize a lower bound on the likelihood of clean data by predicting the original tokens from the noisy versions. During inference, while DLLMs are theoretically designed to randomly unmask tokens, we often use specific strategies to decide the order of unmasking. For instance, the DREAM model selects tokens based on the lowest uncertainty, while LLaDA focuses on the highest probability, known as confidence-based decoding. These adjustments allow diffusion models to compete with autoregressive models in generating quality text. However, when we consider both quality and speed, current open-source DLLMs still lag behind their autoregressive counterparts. Our findings indicate that while DLLMs can achieve competitive quality, their generation speed is significantly slower. For example, to perform well on the GSM-8K task, DLLMs need to generate 256 tokens in 256 steps, which is inherently sequential. Reducing the number of steps can improve speed but often at the cost of quality. Interestingly, we find that a simple left-to-right decoding approach yields good results in many cases, including the best performance on GSM-8K. Next, we discuss the transition from sequential to parallel sampling. By fixing the number of tokens to generate in parallel during each iteration, we notice a clear trade-off between the benefits of parallelization and the quality of the generated text. This trade-off is evident in open-source diffusion models like DREAM and LLaDA. We utilize a specific noise schedule that allows us to denoise from left to right, which is similar to autoregressive sampling and can provide an exact likelihood. To enhance parallelization, we can decode multiple tokens at once from groups of a certain size. However, while this speeds up generation, it can lead to lower quality due to the assumption of independence among the tokens in a group. We observe that as we increase the number of tokens generated simultaneously, throughput improves, but accuracy tends to decline. Therefore, we face a trade-off between speed and quality. Our key insight is that instead of fixing the number of tokens, we can adaptively choose how many to generate in parallel, which helps to mitigate the trade-off between speed and quality. In our method, we aim to sample from groups defined by start and end indices. We need to balance two main goals: minimizing the number of groups to enhance speed and minimizing the difference between our adaptive parallel distribution and the autoregressive distribution to maintain quality. Achieving just one of these goals is straightforward. For maximum speed, we could sample all tokens at once, but this would severely compromise quality. Conversely, sampling each token individually would ensure quality but would be very slow. Due to architectural limitations, sampling auto-regressively from a diffusion model is also slow and cannot utilize caching effectively. This distinguishes our approach from speculative decoding, as computing likelihoods in a diffusion model is inherently slower. We argue that our adaptive parallel decoding method can successfully achieve both speed and quality. Section Summary. In this section, we explore discrete diffusion language models, DLLMs, as a non-autoregressive alternative for language generation, highlighting their iterative refinement and the trade-offs between generation quality and speed. We propose an adaptive parallel decoding method that balances the need for speed and quality by dynamically selecting the number of tokens to generate in parallel, aiming to improve throughput without significantly sacrificing accuracy. Section: Adaptive Parallel Decoding. In this section, we discuss adaptive parallel decoding. We assume we have a small autoregressive model that can evaluate the likelihood of sequences simultaneously. While our diffusion model computes probabilities for individual tokens, the autoregressive model calculates joint probabilities, which helps us understand the relationships between tokens. For simplicity, we will not mention the model parameters. To choose a set of tokens, we focus on a specific problem. Given samples from our diffusion model, we need to select a number of tokens that are close to what the autoregressive model predicts. We cannot directly access the autoregressive model because evaluating its likelihood for each token would slow us down. Instead, we use a smaller, less accurate model that can quickly evaluate likelihoods in parallel. To approximate the autoregressive model, we define a target distribution that helps us decide how many tokens to accept. This target distribution should meet certain criteria. If the diffusion model assigns a probability of 1 to a token and the autoregressive model assigns a probability less than 1, then our target should also assign a probability of 1 to that token. Similarly, if the diffusion model gives a probability less than 1 and the autoregressive model gives a probability of 1, our target should again assign a probability of 1. The first property is based on the idea that if the diffusion model gives a probability of 1 for all tokens, then the joint distribution from the autoregressive model will also be 1. The second property is harder to justify formally, but we assume that our smaller model reasonably approximates the joint distribution, making it sensible to accept tokens with a joint probability of 1. We create a mixture of the diffusion model and the autoregressive model, defined by a hyperparameter that adjusts the weight given to the diffusion model. We then establish acceptance criteria based on our target distribution. We use a universal coupler, which is a function that allows us to sample from our distributions in a way that maintains consistency when the distributions are similar. For categorical distributions, we can use the Gumbel softmax trick as our universal coupler. In our algorithm, we first sample from the diffusion model using this trick, and then we sample from our target distribution. We accept tokens that match until we find a disagreement. We always accept the first token proposed by the diffusion model. Our algorithm takes as input the diffusion model, the small autoregressive model, and a tunable parameter. When this parameter is set to 1, we accept every token from the diffusion model. When it is set to 0, we only accept tokens that the autoregressive model accepts. It's important to note that rejection sampling cannot be parallelized like our method. In rejection sampling, if a token is rejected, we must recompute its distribution based on accepted tokens. Our method, adaptive parallel decoding, does not require a fixed look-ahead window and allows for flexible parallel sampling lengths. Our sampling algorithm is adaptable to different implementations of the diffusion and autoregressive models, but we can use architectural optimizations for speed. For instance, when calculating joint probabilities, we can use caching to avoid redundant calculations. The only requirement for the diffusion model is that it can sample from marginal distributions in parallel, and if it is a transformer-based model, we can achieve even greater speed. Section Summary. In this section, we introduce adaptive parallel decoding, which utilizes a small autoregressive model to efficiently compute joint probabilities and select tokens based on a target distribution, allowing for parallel sampling without the need for a fixed look-ahead window. Our method balances the contributions of a diffusion model and the autoregressive model, enabling flexible and rapid token acceptance while maintaining accuracy in modeling dependencies. Section: Recompute KV window. In this section, we focus on improving the decoding speed of our method by using centered sampling as our main strategy. However, we also aim to enhance the overall performance of diffusion models by considering architectural elements. We implement KV caching for tokens that are outside a defined sliding window. For more details on KV caching, we refer to the appendix. Although using KV caching with a diffusion model that employs bidirectional masking can lead to unexpected behaviors, we find that it does not significantly affect performance. This is likely because tokens that are far from the most recent token have minimal attention weight, meaning their inaccuracies do not greatly impact the overall attention calculation. Next, we introduce the concept of maximum masked lookahead. Since we sample from the diffusion model in a left-to-right manner, we can take advantage of having a long sequence of masked tokens at the end. We set a maximum length for this masked suffix. Reducing the input size can significantly speed up the attention computation, which has a quadratic complexity. However, adjusting the size of the masked lookahead can influence the output distribution, particularly the probability of the end-of-sentence token. We find that tuning the maximum masked lookahead allows us to achieve faster processing with minimal loss in quality. In our experiments, we define 3 adjustable parameters: the multiplicative mixture weight, which affects throughput and quality; the recompute KV window, which also impacts throughput and quality, and the maximum mask lookahead, which similarly influences both factors. Our goal is to analyze how these parameters affect speed and generation quality. For our experiments, we utilize the Dream7b Instruct Diffusion model and the Qwen 2.50.5b autoregressive model, both of which perform well on various benchmarks. Since Dream7b is derived from Qwen 2.57b, they are likely to have similar distributions, and they share the same tokenizer. Although our method could theoretically apply to LLM7b, it uses a unique tokenizer not compatible with existing autoregressive models. In terms of experimental setup, we run our models in BF16 precision on a single NVIDIA A5000 GPU connected to a server with AMD EPYC processors. We follow the LM evaluation harness for benchmarks, with some modifications, and evaluate on GSM 8K, GPQA, and math. To analyze trade-offs, we vary each parameter individually to see how it affects performance. We later plot the parameters together, showing the accuracy on GSM 8K and the throughput measured by the number of tokens generated over time. Our findings indicate that adjusting the multiplicative mixture weight allows us to balance speed and quality. With a small weight, we generate fewer tokens but maintain high quality, achieving over 5 tokens per iteration while keeping accuracy close to that of generating 1 token at a time. As we increase the weight, accuracy decreases slightly, but not drastically. In contrast, increasing the number of tokens sampled in parallel leads to a significant drop in quality. Our method allows for higher token acceptance rates without sacrificing quality by dynamically choosing when to sample in parallel. We also examine the impact of changing the recompute KV window and find that reducing it can lead to speed improvements with minimal quality loss. Finally, we look at how altering the maximum mask lookahead affects speed and quality. We discover that while decreasing this parameter increases throughput, it can also significantly impact quality due to shorter generation lengths. Overall, we see that each parameter presents a unique trade-off between speed and quality, and we believe that allowing users to adjust these factors during inference is a key advantage of our approach. Section Summary. In this section, we explore methods to enhance the decoding speed of diffusion models by implementing KV caching for tokens outside a sliding window and adjusting parameters like the maximum mask lookahead, which allows us to balance throughput and generation quality. Our experiments reveal that while tuning these parameters can significantly improve speed, it often comes at the cost of quality, highlighting the importance of flexibility in managing these trade-offs during inference. Section: Pareto Frontier. In this section, we discuss the Pareto frontier, which defines the optimal configurations when balancing conflicting objectives, specifically speed and quality in LLM inference. A configuration is Pareto optimal if we cannot enhance one objective without negatively impacting another, like increasing latency. The Pareto frontier includes all these non-dominated configurations, marking the limits of achievable performance. We illustrate this frontier across various tasks and model setups. For instance, Dream7b with a basic configuration decodes 1 token at a time, resulting in low speed and high density. This setup also sets an upper limit on the quality we can achieve with other decoding parameters. However, when we apply our ADP configuration to Dream7b, we see a significant increase in speed with minimal performance loss compared to the basic setup. Notably, Dream with ADP outperforms both the autoregressive Qwen 7b and Qwen 0.5b in speed. Even if Qwen 7b utilized speculative decoding with a draft model from Qwen 0.5b, it would still not match the throughput of ADP. Thus, Dream with ADP is Pareto optimal, as no other model can surpass it in both speed and quality. Additionally, ADP shows considerable improvements in latency. Diffusion models have an advantage because they generate fewer tokens within a fixed context window, while autoregressive models can produce longer, less coherent reasoning that may not enhance quality. We also evaluate APD on standard benchmarks and demonstrate its capability to quickly generate responses for more open-ended tasks, as shown in the appendix with examples from persuasive writing prompts. In our findings, Dream 7B with ADP achieves much higher speeds with little impact on performance compared to the basic model. We established that Dream with ADP is indeed Pareto optimal, as no other configuration excels in both speed and quality. We present two hyperparameter configurations of APD, illustrating our ability to flexibly balance speed and quality. In related work, several studies have suggested architectural changes to LLMs for multi-token prediction, such as MaskPredict, Medusa, and Dynamo. While these approaches are promising, our focus remains on multi-token prediction in diffusion LLMs. Other recent efforts aim to enhance the speed of diffusion LLMs, like block diffusion, which allows for KV caching but requires training, unlike our method. Discrete copula diffusion reduces the number of denoising steps during inference but lacks a tunable speed-quality trade-off. More broadly, methods to accelerate LLM inference include cascades, look-ahead decoding, and speculative decoding, which are primarily applicable to autoregressive models. Some works have built on speculative decoding using various architectures as draft models, including any-order autoregressive models and diffusion LLMs. We stress that employing a large diffusion LLM for parallel drafting presents unique challenges that speculative decoding does not address. Lastly, we note that quantization is another promising approach that offers a strong speed-quality trade-off in LLMs.